All right, ladies and gentlemen, we're back. Again, I'm Maurice Woods. These two students right here, Aspen and Odysseus, have been working with Dr. Richard Deet on observing variable stars and identifying exoplanets. So I hope you enjoy their presentation. Okay, good.
Hi, my name is Aspen Riker.
And I'm Odysseus Quarles.
For the past 5 weeks, we've been working with Dr. Richard on determining whether or not the exoplanet TrES-3 is orbiting the variable star TrES-3.
Some definitions. A variable star is a star whose brightness changes over time. This can be for a variety of reasons, either from passing through an interstellar dust cloud or from being orbited by a planet. And this can happen either regularly or irregularly.
An exoplanet just means a planet outside of our solar system.
A transit is when a planet passes between the star in orbit and the observer from pretty much, in our experiences, that's going to be Earth. And this blocks out some of the light from the star.
A hot Jupiter is a large gas giant that orbits extremely close to the star. The yellow circle right here is the variable star TrES-3 that we've been looking at, and the little exoplanet right here is called TrES-3b, and we're seeing if the exoplanet orbits the star.
So, a couple statistics about the star TrES-3. It is a magnitude 12.4 star. The magnitude still is a little bit confusing, so I'll put a diagram in here. A lower magnitude is going to be much brighter than a higher magnitude. So the sun, as bright as it is, about -27. TrES-3 is about 90% the mass of the sun and about 80% the radius of the sun. It is about 1,500 light years away in the constellation Hercules. Red attention and declination are pretty much the way that astronomers look at the sky to try to figure out where things are. This little red attention and declination chart like that. Some fun facts: the closest star to the sun is about 4.2 light years away, it's called Proxima Centauri, and the farthest known object in the universe is 13.2 billion light years away. That's about 1 million times the farthest star we've been studying.
Here's a picture of the variable star TrES-3 and the exoplanet that orbits the star.
Some statistics about the planet TrES-3b. TrES-3b is an exoplanet orbiting the star GSE 03089-00929. Most people just call it TrES-3. TrES-3b is a very large planet crossed by the hot Jupiter, which we mentioned earlier. It is very close to a star, about 2% of the distance between the Earth and the Sun. And it is an extremely large planet, about twice the mass of Jupiter and about 1.5 times the radius of Jupiter. It has an orbital period of just 31 hours. An orbital period is a year, so that's like if every 1 day and 7 hours, 1 year would go by. This is one of the shortest known years of any known exoplanet. And this close orbit causes a fast revolution around the star, but a very long day. It is also causing ozone decay and planetary evaporation. Planetary evaporation is pretty much when parts of the planet's atmosphere are being thrown off by the solar winds. This planet is like Jupiter, it has a similar composition, mostly hydrogen and helium, with trace amounts of noble gases.
It allows us to take pictures of the star. Some places like Spain, Mexico, Australia, everything we use two telescopes in space. AAVSO stands for the American Association of Variable Star Observers, and it allows, it was founded in 1911, and it allows astronomers to coordinate, collect, evaluate, and analyze variable star And it makes studying variable stars astronomers a lot easier. VSO is a free online tool for doing photometric analysis of images. It allows astronomers to easily analyze the photos and collect data and determine how to do different variable stars. It includes the basic photometric analysis tools, and you can analyze photos.
Pretty much how we go with negatives of the images that are taken, and it pretty much all it does is it counts the numbers of black pixels in the star that you are analyzing, then counts the number of black pixels in a star that it knows its magnitude is. You can then compare it then to figure out the magnitude of the star that you're studying. So rather than just jumping into this project, we have a couple of preparations. We watched some informational videos on how to use VSO, the 9-part series. We also practiced photometry with a stuff called video, using mural photos, not photos that we took using Exoplanet. And we made Excel graphs, scatter plots of the magnitude of SVO versus time. We also, for this, we used images from this year and last. This is what an image looks like if you're analyzing it using VSO. Right here in the middle is where you have a target star that can be in green. Then all around it in blue are the comparison stars, which are used to measure the brightness of the target star. And then orange is check star, which is pretty much used to check how accurate the measurements are. So how exactly do we go from the night sky to that? Well, what we do is first we take a picture using our telescope.net, then send over to VSO for analysis. And then we load in the variable star index, which will pretty much tell us what variable stars we can see in this picture. Usually you'll get a bunch of different variable stars, which are listed over here. Also shown here. After that, we bring in the AVSO comp stars, which show up in blue. Then we have to get rid of all of the variable stars except for a target star, because we really only want to analyze one star. After that, we will convert one of the comp stars over to a check star so we can see how accurate we're being.
So a light curve is a graph showing the brightness and magnitude of the star over a long period of time. Here's a picture of a light curve. As you can see, the magnitude of brightness is varying over a long period of time.
So, here's our observations. We observed TrES-3 both while the planet was in transit and out of transit. We took 10 in-transit images and 10 out-of-transit images. The in-transit images were used to pretty much use as control. The out-of-transit images were used as control, and the in-transit images were used for analysis to figure out whether or not there was an exoplanet within TrES-3. Out of transit, we found an average magnitude of 12.4, and the dimmest visible stars are 6.5. Remember, the magnitude scale goes backwards, so a 6.5 star is much brighter than a 12.4 star, and therefore TrES-3 is not visible in the night sky. In transit, we found a minimum magnitude at the dimmest point of 12.4 and a maximum magnitude at the brightest point of 12.35, with an average magnitude of about 12.37. So we can draw a couple conclusions from this.
In transit, pictures appear brighter than out of transit, which should mean that exoplanet.
However, in 2007, O'Donovan et al. Published published an article in the Astrophysical Journal, which stated that they had found and confirmed the existence of the exoplanet TrES-3, which really goes against what we found. So a couple reasons we came up with for the difference in results in our study, the study that Aspen did in 2007, is that we had very limited data sets. We only took a total of 2 image series, only 1 in transit and 1 out of transit. They were only 10 images. This could lead to a very large black precision. And we also had very high error values, up to 0.013 in some of the in-transit data. If you want to be really accurate, really sure that people are going to accept your data, you're going to want an error value around or below 0.09, excuse me. And we also may have inaccurately timed the imaging run that we did in transit, which means that we probably took the images almost an hour early. With a transit of only 1 hour and 45 minutes, an hour early will mean that we won't be taking images during the transit.
So, some changes in procedure that we would do were to take more observations for control and transit data, and to use only one telescope instead of 2 different telescopes. Technology. We'd like to thank our mentor, Dr. Judy, for helping us with tax sizes.
We'd also like to thank our advisor, Maurice, for also helping us in the past 5 weeks. I would like to thank my sponsor, Noble Energy.
We'd also like to thank for being available for any questions or concerns that we have. I'd like to thank one of my sponsors, Bell Aerospace and Technology Corporation, and Exoplanet Foundation for funding the program.
We would also like to thank Crystal Miser for keeping us on track, and we'd also like to thank Lori Ball for making SSI such a fun place to be, and we'd like to thank USC for allowing us to stay here. Any questions? Jesse?
Okay, so you said that you could have the variations in the light. You can also raise it. So how would you be able to tell if it was a planet that was the cause compared to passing behind it, which is stellar dust cloud?
Okay, so the question was, how would we be able to tell the difference between variations from passing through an interstellar dust cloud and a planet passing in front of a star? That is because when a star passes through an interstellar dust cloud, the changes will be very irregular, and if it's being orbited by a planet, it'll be in a way just like the light curve that shows you, just going up, down, very consistent. Charlie?
Why does an in-transit reading of the stars require when it's not the black planet that there should be an exoplanet on the star?
Well, generally, if there's something in front of the star that's supposed to be dimmer, it's supposed to be brighter. So, yeah. Chip?
How are you able to then compare, like, if you have a planet with an exoplanet, or a star with an exoplanet orbiting it, how do you actually read the magnitude? Is it actually dimmer than without any color?
Yeah. Well, as I explained in my other slide, what we do is we don't do anything, but the program pretty much counts the number of pixels in the target star, and counts the number of pixels in a star that we know the magnitude of, and then just compares that. So it doesn't care whether it's kind of in front of it or not, it'll just figure out what the magnitude is.
And does the magnitude of the star change as, like, as the number changes?
Yeah.
It does.
That's definitely effective.
Does it mean that the star that you compare trades 30 will be around the same distance away from Earth?
Yeah. I'm not quite sure. Any other questions? So, Chelsea? could be on the other side. Any other questions?